Welcome to EDU World Space.
When a photon strikes a piece of metal, the photon's energy will cause an electron to be ejected if the photon's energy can overcome what's called the work function of the electron. The work function is the amount of energy it will take to knock the electron off of the piece of metal. Now, we can write this as that the energy of the photon, E sub p, is equal to the work function psi plus the kinetic energy of our electron. So you can see that the energy of the photon goes into overcoming the strength with which the electron is held to the metal, and then the leftover goes to the kinetic energy of the electron. So, we're told that psi is equal to 2.9 electron volts in this problem. 2.9 electron volts is equal to 4.64 times 10 to the minus 19 joules. So we're told what would be the minimum wavelength of a photon that could knock an electron off the piece of metal. Well, the minimum would be the case where the electron is ejected with zero kinetic energy. So this would be 0, which tells us that we just want the energy of the photon to be equal to the work function. That will be the minimum case for knocking off an electron. So the energy of a photon is hc over lambda, where h is Planck's constant and c is the speed of light. And so this is equal to psi. So we can solve for lambda, and we get that lambda equals hc over phi, the work function. So this will be the minimum wavelength. This will be the longest wavelength such that the photon has enough energy to eject the electron. So we can plug in our numbers to this. So we can plug in our numbers, and we get that lambda equals Planck's constant, 6.626 times 10 to the minus 34, times the speed of light, which is 3 times 10 to the 8th meters per second, over our work function in joules, which is 4.64 times 10 to the minus 19 joules. And this gives us that the minimum wavelength is equal to 4.28 times 10 to the minus 7 meters, or 428 nanometers.